Hello everyone, this is your tutor AB. Today we're going to be solving a problem from the IB Physics May 2016 Paper 2 examination. This is an older problem, but it is really helpful to study the older problem, so we'll be doing it today. This problem is almost 9 years old by the time the May 2025 questions come around. Okay, the Sun has a radius of 7 into 10 to the power of 8 meters and is a distance of 1.5 into 10 to the power of 11 meters from the Earth. The surface temperature of the Sun is 5800 Kelvin. Show that the intensity of the solar radiation on the upper atmosphere of the Earth is approximately 1400 watt per meter square. Okay, so if you look at your data booklets, you're going to have two equations. One is for the brightness, which is nothing but the intensity. So brightness is equal to the luminosity of the star over 4 pi d square. And we have another expression for luminosity, which is the power output, which is basically sigma a t to the power of 4. And this is obviously ignoring the albedo and the emissivities. Okay. Now, how can I calculate the intensity felt by the Earth due to the Sun? So, what do I mean by this? So, for example, if we have the Sun, which is a star, and it has some energy emitted, and Earth is at a distance away, how much of this Sun's energy that is emitted is actually felt or absorbed by the Earth, right? So, well, how can I explain this is this way? Okay, so this is like a small diagram to just kind of illustrate the scenario, because obviously not all of the energy emitted by the sun is absorbed by the earth, because this energy is spread out, right? So how can I solve this? Now B is what I'm solving for, the intensity at earth, the surface of the earth. So I can rewrite B to include this term for luminosity. So B is equal to sigma a t to the power of 4 over 4 pi d square. Now, this term right here is basically the power output of the sun. Okay? And this bottom term here is we can call it like the surface area, right? That term right there is the surface area through which the sun's energy is spread. So these are some rough definitions for these two terms, and when I divide the power output of the sun by the surface area through which the sun's energy is spread, I get the brightness. I'll get the brightness at the point of Earth. Okay, because instead of d, I'll be writing the distance of the sun from the Earth. So what I'll do, I'll move this diagram up here so you can refer to it, but so I can have some space to write. Okay, so how can I calculate this? Well, I know all the values, so simply just plug in. So the Boltzmann's constant is 5.67 into 10 to the power of negative 8. Okay, so area, this is surface area of a sphere. Now the surface area of a sphere is 4 pi r square. So 4 pi, and now what is the radius of the sun? Because on the top is the power output of the sun, so everything due to the sun. So the radius of the sun is that much, 7 into 10 to the power of 8 meters. So that's whole square, 4 pi r square, times by the temperature of the sun, 5800 Kelvin. But that's to the fourth power. Like so. Then this whole thing divided by 4 pi and d square. So the distance from Earth from the sun. So 1.5 into 10 to the power of 11 the whole square. Now 4 pi and 4 pi will cancel, and so we simply just need to put this in our calculator. Now what do we get? Let's see. So 5.67 into 10 to the power of negative 8 times by 7 into 10 to the power of 8 the whole square. Okay, times by 5800 Kelvin to the power of 4 over 1.5 into 10 to the power of 11 the whole square. So I get the sun's intensity is approximately 1397.36 Kelvin at the point of Earth, and that's approximately equal to 1400 like they've asked. So this question is done. Okay, the albedo of the atmosphere is zero point 0.3. Deduce the average intensity over the entire surface of the Earth is 245 watt per meter square. Now, look. So, at the point of Earth, 1400 watt per meter square intensity is incident on the planet, right? But the thing is, not all of this is actually absorbed. And what do I mean by this? Well, the Earth is a sphere, and only a circular projection of the Earth actually absorbs this incoming intensity. Okay, so if only a circular projection of the Earth absorbs this intensity, we can basically, there is like a derivation for this, but you can skip over it. So you can basically divide the intensity on the Earth due to the sun, which is like 1397 over 4. Okay, because we're basically saying that the Earth, if the sphere can be split into 4 portions, 4 projections. Out of this, only one projection actually receives this incoming intensity. So if I divide these two together, I'll get 1397 divided by 4. That's about 349.25 watt per meter square. Now this is the average intensity absorbed by the Earth over the Earth. Okay, this is the average. But we know that not all of this will actually be absorbed. Why? Because the Earth, the albedo, the Earth or the atmosphere of the Earth has an albedo. The albedo is how much incoming energy is reflected, the portion of the incoming energy that is reflected. So we can say that 0.3, so about 30% of the incoming energy will be reflected. So about only 70% remains. So if I simply do 349.25, which is the energy, the intensity over the Earth, times by 70%, which is 0.7, that's how much of this will actually be absorbed, I will get 244.475. So 244.5 basically, which is approximately 245 watts per meter square. That's the average intensity over the entire surface of the Earth. Now they ask us to estimate this average surface temperature of the Earth. Now we can just simply use this equation from before. We know that L is equal to sigma A T to the power of 4. Okay, now this is power and that's surface area. So we can basically say that L over A is equal to sigma T to the power of 4. Now what is L over A? This is nothing but the intensity. Okay, and we calculated the intensity before. The intensity which is going to affect the temperature of the planet will be this right here. This is what we care about. So we can simply sub this in. So 245 is equal to sigma T to the power of 4. Okay, now so basically if we rearrange for T, we can get the fourth root of 245 over sigma comes out to be T. Now let's put this in our calculator and see what we get. So 245 over 5.67 into 10 to the power of negative 8 whole to the power of 0.25. That comes out to be, the temperature of the Earth comes out to be 256, about 256 Kelvin. Okay, thank you for watching. Please like and subscribe. If you have any questions, leave it down below and I'll answer it as soon as possible. Thank you for watching.